Hi there, my name is Steve Rogers and I work in the mining business of Golder, worldwide consulting business. I'm based in Golder's Vancouver office in beautiful British Columbia. I'm also a member of Golder's FracMan team, which is Golder's Discrete Fracture Network modeling tool, and all of the work I'm going to show you today has been carried out within our FracMan software, as well as some associated tools. What I'm going to be talking about is how we can use DFN models to provide a basis for improving reliability in slope designs. We'll look firstly at some issues associated with DFN modeling in general and slope engineering more specifically. Then we'll look at DFN models in bench design, and finally some exciting work we've been doing integrating FracMan DFN models of inter-ramp slopes and integrating these with a custom 3D limit equilibrium tool for improved inter-ramp design. At the heart of DFN modeling is a desire to be able to represent the rock mass fabric in 3D space explicitly rather than implicitly, like this. We can transform geological and geographical data into quantitative parameters that describe the fracture network and its variability in space. As this is a stochastic modeling approach, we need to define the underlying distributions of these key geometric properties, namely orientation, size, and intensity, as shown here. But also, depending on your application, they might also include hydraulic or strength properties. Now, there is a rich array of modern data available for constraining your DFN model, including advanced photogrammetry techniques, borehole televiewers, etc. But that is the subject of another talk, really. With DFN modeling, we want to replace the inherent conservatism of implicit or simplified approaches with a greater degree of realism. For a simple example here, we have a borehole defining fracture frequency and also orientation properties, along with mapping data that defines the length distribution of structures. We might want to define key deterministic explicit major faults here, and then stochastically generate the smaller structures around the fault. And here we have a DFN fabric. A really important aspect of DFN modeling is the need to understand that all measurements of fracture intensity have an implicit minimum size measurement associated with them. Structures that we see in core may have a minimum size in the order of centimeters. Bench mapping data may be recorded above 0.5 meters or more. And of course, mine scale wire-framed major structures may only exist above 100 meters or even more. As such, all of these different measurements will have a different intensities because they have a different minimum size. Therefore, an important part of the modeling process is to adjust all our intensities to represent the correct minimum size of structures. As can be seen by these examples on the right, by representing only larger and larger structures, the intensity of fractures in the DFN model goes down. Of course, when we build a DFN model, it's really important to demonstrate that it's a good model, and we do this through the process of simulated sampling. This involves sampling our model with boreholes and mapping in the same way the actual field data was collected. This example on the screen shows a comparison between the target and simulated fracture count from a DFN model, showing a very good agreement. In the middle, we have the actual and simulated orientation data from the model. And lastly, we have a comparison between mapped structure lengths in the field in red and simulated drift mapping in blue. And we can see the goodness of fit between the DFN model and the simulated sampling of that model is good. Many of the analysis tools that we use in mining represent fractures as ubiquitous, infinite, and independent, and that is not the case. In DFN modeling, we want to seek to represent the fractures as realistically as possible, and that means it doesn't have to be a simple case of putting fractures in a box, like many people might have seen in synthetic rock mass models. This might be reasonable for bench scale analysis, but representing the structural geology and its complexity becomes very important to slope stability at the interramp scale. Some simple conceptual arrangements of fractures might be randomly organized, they might be deformed, they might be ordered and arranged into more regular layered systems, or they may be clustered around major structures, or a combination of several of those. Capturing this in the model is very important. Failure to do this leads us to what I call the frog in the blender paradox. If we consider the scenario of two blenders, each with one frog and 1 liter of water inside them, with one of the frogs blended, statistically they are identical. However, only one of the frogs can still croak. So we want to make sure that our model represents the unblended frog with the order preserved, because statistics plus order equals realism. Modern DFN tools such as FRACMAN allow us to generate more realistically constrained models. The example on the left represents a layer-bound jointed system whose joint density is controlled by the thickness of beds and whose orientation is controlled by the relative orientation of the folds. This slope model could represent a pit slope from the iron ore mines of the Pilbara region of Western Australia, for instance. On the right, the model shows a slice through a large open pit where the presence of bedding faults are seen to be following the light blue deformed limestone beds within the pit wall. Can we add more structural reality to our slope analysis is a recurring question that we must ask and answer. So now let's look at the issue of bench stability. Most people would agree that conventional bench design methods are highly conservative in nature, with bench performance often exceeding those designs. However, when we consider the problem using a true DFN model, we can start to understand something about the probability of wedge formation rather than simply the possibility, as is the case in simple wedge analysis. In a recent benchmarking exercise between a conventional wedge analysis approach such as S-wedge and FRACMAN on a simple single wedge case, the results are seen to be identical as seen in the lower left graph, showing probability of failure versus bench face angle. However, when we carry out the same analysis using a true DFN model, we see that there is an increase in recommended bench face angle of approximately 8 degrees for the same probability of failure as seen in this right-hand graph. Again, this is because we are considering the probability, not the possibility of failure. An important development in DFN analysis techniques over the last few years has been the transition to identify complex blocks in kinematic analysis rather than just simply the free face attached blocks. If we consider the image on the screen, the case on the left with just 2 faults shown in yellow would yield a single large unstable wedge in red. In the middle case, these 2 faults are embedded within a broader joint fabric, and because traditionally the kinematics are evaluated from the blocks attached to the free face, the stability of the joints defined blocks are stable, rendering the fault-defined wedge also stable as it sits behind. However, in recent times, the search algorithms have become more complex, allowing the blocks to be searched backwards into the rock mass, allowing the stability of all the blocks to be determined simultaneously, allowing the larger unstable volume to be identified. So let's now consider the case of interramp analysis. So now we're thinking about a stack of, say, 10 to 20 benches. The analysis approach hasn't fundamentally changed very much for many years. At the local scale, failure mechanisms tend to be structurally controlled, and kinematics provides a reasonable answer. However, at the interramp scale, analysis must consider a composite and complex failure mechanism, including both kinematic and rock mass. So these need to be captured efficiently to allow a range of design options to be considered. Over the last couple of years, we've been developing a combined DFN limit equilibrium approach that we believe delivers this requirement, offering a step change in interramp design approach. The start of the interramp analysis approach is based around building a realistic DFN model at the interramp scale, as highlighted at the beginning of this presentation. These models are built up from available geotechnical and structural data that define properties of intensity and orientation and size of the structural fabric. In the case illustrated here, based on work carried out at the Bingham Canyon mine, this particular model is showing fabric of the scale of approximately tens to hundreds of feet in size. This model is 700 feet wide and 700 feet high, representing 14 50-foot benches. Having built the DFN model, multiple realizations are generated and blocks forming within the slope are identified for a range of differing interramp slope angles and orientations. These large multi-bench scale blocks seen on the right, here in green, are then passed to a 3D limit equilibrium tool that evaluates each block's stability, including both rock mass component and water, using a custom slip surface solution. This approach together results in the evaluation of the stability of thousands of different blocks and can be compiled together to derive probability of failure distributions for all interramp angles tested. Let's just consider these multi-bench complex blocks in a little more detail. For the example here on this 700-foot design slope, it shows multi-bench blocks extending over up to approximately 8 benches or more. They are largely kinematically stable as their shape renders them typically locked in, apart from a small number of conventional planar and wedge failures seen in red. In the example on the right, we can see that with increasing interramp angle, there is an increasing proportion of these complex rock blocks being formed on the slope. So this clearly represents a potential precursor to slope instability. Let's examine the stability of a complex block in a little bit more detail and how we can evaluate its stability. The example shown on the left represents a complex block seen from the front and from the back, and also in section in the large image in the middle. The blue and black lines here represent fractures that are defining the block within that section. Evaluating the stability of these blocks requires a custom solution, as there are many different ways that this rock mass volume can fail, including both kinematic and rock mass components. The first failure surface that we can evaluate is this one shown in red, running along the back and daylighting out through the rock mass buttress at the toe. Alternatively, it could slide along this upper slip surface. It could slide along the slip surface, daylighting through the rock mass buttress, and also involve shearing a notch of rock mass. In this case, the stability calculation will be weighted according to how much rock mass and how much fracture was involved. Lastly, the upper portion of the block could fail along the slip surface and through the rock mass toe. So these individual composite blocks are identified and analysed from multiple DFN realizations. Each inter-ramp angle and orientation is analysed approximately 100 times, resulting in a total block count in the order of tens to hundreds of thousands of blocks to be computed. However, the limit equilibrium solution can analyse each block in a fraction of a second, resulting in an efficient solution. The results of all realizations are aggregated together to develop statistics as a function of both inter-ramp angle and slope azimuth, with inter-ramp recommendations being based on a specific design acceptance criteria. Another application of the identification of these large multi-bench complex blocks is in the derivation of block probability maps at the scale of the pit wall, as seen here. Obviously, if we consider these large multi-bench blocks as precursors to potential instability, areas where more of them form should be more likely to experience potential instability. If we repeat the analyses at the wall scale, as shown here, building multiple realizations of the DFN model and identifying where the blocks form, we can then combine the results of multiple realizations by adding up the number of cells in a grid where blocks are located to produce these heat maps, as seen on the right. In the case shown here, a number of these areas with higher block probability locations seen in the hot colors result in observed instability during mine life. In summary, modeling the rock mass fracture system using DFN codes such as FRACMAN in conjunction with realistic 3D structural modeling have a number of advantages. It gives us the flexibility to realistically model a wide range of fracture scenarios, adding real structural geology to our geotechnical evaluation. It gives us the ability to build constrained and conditioned models built up from 1D, 2D, 3D data sources. It allows us to realistically reproduce observed fracture properties without the need for excessive simplification. And perhaps most importantly, it allows us to replace conservatism with realism in our models. And that gives us an opportunity to develop designs with greater reliability that will be more cost effective. And at the moment, who wants to leave money on the table? Thank you.